All right. So, yeah, welcome everyone. This is the seventh interactive session for the course of machine learning. I am Shagni Kacharia. I am a student in IISc Bangalore, and I'm serving as a TA for this course. So, let's start today. So, I wanted to discuss week 7 content, but like there is not a lot of mathematical concepts or anything which I can discuss. It's mostly the professor was sharing a lot of facts. I don't think I have anything separate to discuss from that. So if you guys have any doubts in general, you can ask me. We'll go through those first, and then we'll try to cover a small example on binary classification, right? We'll try to code a binary classifier from scratch and see how it works, see all the all the mathematical concepts which you have learned over this course being put into action, so to speak. So yeah, please, if you have any doubts, you can start asking me.
Um, Hi, I'm Tejaswi. I had
Hey.
one of the probably the assignment questions which were provided. I was not very clear on how this like the solution, how the solution was
Okay.
I
Can you
was
tell me which question you're talking about?
Yeah, sure. It is week 6, assignment 6.
Just a second, I'm opening it.
Sure.
Yeah. Yeah. Which question?
Give me a second. I'm just reaching over there. So it is essentially basic. I think question number 13.
Okay, just give me 1 second. I need
Yeah,
to sign into NPTEL
sure.
again.
Yeah, take your time.
Yeah. Okay. Question number 13. You said, right?
Yeah.
Question
So I
13.
basically thought it was just a matrix multiplication, and like based on the stable unit states, you'll have to substitute -1 or 1, where depending upon, because they are the only stable states.
Yeah.
Uh, but for some reason, like I had answered it as the first one, like or option A. But I think the accepted answer is 111. So I was not
Yeah. Okay.
sure.
So in this case, you can see here that like they've already done most of the computation for you.
Yeah,
So X transpose X is your weight matrix, and you divide that by 3 basically.
exactly. Yeah.
You get your final weight vector,
Hmm.
and when you multiply your test case, you'll
Yeah.
get some numbers, right? And there, uh, so apply a threshold function with threshold equal to 0. So yeah, so during this multiplication, I think I've solved a similar problem. Let me see
So
once.
it is like a row into column, and because two of the other digits in the row, they are 0. So it is basically I would get 1 by 3 1, and
Yeah, that's right.
yeah, and then the stable unit states are -1 and 1.
Yeah,
So it will be 1 -1 1, right?
just a second. Uh, I'll answer your question. There's some more people
Okay,
trying to
sure,
join.
sure. Okay,
Yeah, sorry. Yeah, so it was 1 by 3 1, right? So
yeah,
that's what I get after the multiplication.
yeah.
And now what I need to do is apply a threshold function with threshold equal to 0 in all elements, right? So in this case, you would get, yeah, you would get 1 minus 1, 1. That
Because the
is right.
stable unit states are
Yeah, that's
minus
right.
1 and 1, right?
That's right. That's right.
For some reason, the accepted answer is 1, 1, 1 rather than
Uh,
minus 1, 1 actually.
okay, just give me 1 second. I need to cross check something,
Okay.
which I so okay. Yeah, I mean, yeah, that's right. You're right. It might be that the answer key was wrong in this case. Yeah, but your reasoning is correct. Yeah,
Okay.
that's
Thank you.
that's right. Okay. Any other questions you guys have?
So, one,
Yeah.
is there a way that we can approach back to anyone probably who look after that particular thing so that it doesn't happen
Uh,
for other students, or probably
okay.
that
Okay.
takes into
Yeah,
consideration?
I'll actually try to report this to the NPTEL team,
Okay, thank you.
saying that there might be a problem here. So they might, reevaluate that assignment with that question. So
Thank
you
you.
might get an updated score. I'll talk to them about it. I'm not sure what the exact
Sure,
process.
sure. Thank you.
So, sure. Okay, guys. Any other questions you have, or I'll move to the example which I've prepared for you guys. Okay. Since you guys can also type in the chat, by the way, if you want. I'll keep the chat open. So if you guys have any questions in between, also, then please you can stop me and ask a question. Okay. So I'll move to the example. So we have, like you have studied binary classification through this course, and so the I mean, I'm not going to explain the basics of binary classification. I just want to clear a few things, and then we'll move to the example. So, in the course, you were told that the cost, so the cost function which we use for binary classification was something like, half of t minus y square. So this is just and you can like if you have multiple examples, you can sum over them and take mean, and so this is basically mean square error. So you were told that we can use this. We can definitely use this for binary classification, but the importance of choosing a proper cost function is that you need your, so when you have a cost function like this, and you have your certain if you say I have two weights like this, I'm going to draw a 3D plot. So this is my cost, right? And I have two varying weights which I can vary. So this is W1, this W2. So W1, W2 are my weights. I can vary them however I like. Usually there will be a lot more weights, but I am only stuck to like the maximum I can draw is a 3D plot. So what I want is, so this J versus W1, W2 graph to be some sort of simple, like a graph with one global, so it will form sort of a surface, and I'm hoping it will have this only one, like a global minimum over here, and I'm hoping that like through my optimization process, through gradient descent and everything, I can start like slowly approach this point, and I'll get the minimum cost for for a certain for certain values of w1 and w2. So this is always the goal with a cost function. So whatever cost you choose, you must consider if like I mean, you can't say for certain from the beginning, but it is always good to have just a very simple, just a very simple surface with just one, ideally one global minimum where my optimal solution lies, right? So what we have found, not what we have found through experiments, is that like this cost here, the mean squared cost, this does not hold up very well for binary classification or any kind of classification problem, because it creates a lot of these local minima, right? So there'll be a small minimum over here somewhere. So say there's a small minimum over here, there's a small minimum over here somewhere. Okay, and there's a chance that my weight gets stuck here and is never able to recover and come back to this global minimum, right? So I'm making a mess of this 3D graph, but please bear with me. So mean squared error is not really a good choice. So the usual cost which we use is for only for one training example I'll show you. The cost which we tend to use is it's minus of t log. So yeah, by the way, t is my target. So this is my target value, and y is my predicted value, which I get from my classifier, right? So it is t log y minus 1 minus t log of 1 minus y. Okay, this log is it's so by log I mean the natural log. Uh, you can write ln if you want. And this is log base e, not log base 10. Okay, so it's written in this form, and it's been found that if you use this cost for a classifier, the cost versus weight like map, like this surface here which I've drawn here. This is a very simple surface, so it has only it has like for very simple cases it has like one global minima where all the weights can converge. So this is a good choice for cost. Now the thing is, we also want to back propagate and find the like find how the cost varies with the weights, right? So we want to find del j del w for this cost, right? For this j, uh, I'll erase this previous j and write something else. So okay, big eraser. So I'll write L here. Okay. So right. So we need to find this del j del w. Okay, and I'm not going to go through the entire process. I'll quickly give an overview. So what I have is, so I have this uh, my binary classifier unit, and I have all of these inputs coming in, right? So there can be any number of inputs, right? So x1, x2, x3, all the way till xn, say. Okay, so I have n inputs, I have n weights, right? So and here I will get my y. So how I get y is, so first what I'll do is I'll define something called z. Z is equal to w1 x1 plus w2 x2 plus all of this till wn xn plus bias term. Okay, so okay, so this is z, and my y will be sigmoid of z, right? So sigmoid is usually given this symbol sigma, right? And so the formula for sigma of z is 1 by 1 plus e to the minus z. Okay, so this is what I have. Now what I need to do is I need to find so I need to find del j del omega, del j del w, right? Sorry, I keep saying omega. So this is equal to del j del y times del y del z times del z del omega, del w, right? So you see that I have a relation of z with respect to w, which is given by this one, right? I have a relation for y with respect to z, which is given by this one, and I have an expression for j with respect to y, which is given by this, right? This. So I can find all of these three derivatives separately. So del z by del w, this will just give you, if you calculate it. So if you're calculating it for omega, for w1, then this del z by del w1 is x1, right? Del z by del w2 is x2. Then it's just the corresponding x value, the corresponding input. So we will not be very concerned with this term. So let us find these two derivatives, right? So I'll change colors for, uh, so let's say I use blue for this one, right? So del j by del y, right? So okay, I have this expression right here. So what will the derivative be then? So t is a constant, by the way. So t is just the target value, it is a constant. So this will be t by y minus, again, 1 minus t by, oh sorry, by the way, this is a plus, not a minus, sorry. So I have plus here for now. Okay, 1 minus y. But if I, so this, I differentiated with respect to 1 minus y. If I differentiate this with respect to y, this will be minus 1, right? So what I get is, so I'll take common denominator, y into 1 minus y, right? And the top it will be t to 1 minus y plus, sorry, this will become minus, this will become minus 1 minus t into y, right? Yeah. So if you do this, then what you get is, so this is minus of t minus ty minus y plus ty, right? So these two are gone, and I get y into 1 minus y. So this is equal to y minus t divided by y into 1 minus y. Okay, cool. So we are done with this first derivative. So let's see, I'll use green for the second one. So del y by del z. Okay, so this is basically the derivative of the sigmoid function, right? So this is, so what I have is del z of 1 plus e to the minus z minus 1. So if you do this derivative, I'm just going to do it quickly. If you do this derivative, what you will get is e minus e to the minus z by, no, you, the minus will get deleted. So, e to the minus z by 1 plus e to the minus z square. Okay, so this is not a very good looking form. What I can do is, so if you see here, uh, so what I'll do is I'll write it as 1 by 1 plus e to the minus z into e to the minus z by 1 plus e to the minus z. Now if you look at this term is y, right? This term is the sigmoid function. This is sigmoid of z, right? And I know, I call that as y here. Okay, so this is y, and this term I will add a new slide, and we'll see. Okay, so this this okay. So where were we? Okay, so this we are talking about this term right now. Change back to red. Sorry. So this term over here, that will be, so e to the minus z by 1 plus e to the minus z, right? So I can write this as, what can I write it, 1 plus e to the minus z minus 1 by plus e to the minus z. So this thing over here, this is equal to 1 minus 1 by 1 plus e to the minus z, right? So again, and this is again y, this is equal to 1 minus y, right? So finally del y by del z, this becomes equal to y into 1 minus y. Okay, and finally for the last term I told you del z by del w, so this is equal to, so del w, j, let's say, I won't put j, I'll put k. Okay, so this is equal to the corresponding x, right? So now I have all of these three terms, right? So I can write del j del w equal to, first term is del j by del y, right? So that came out to be this over here. So this is y minus t y, y into 1 minus y. Okay, then the second term is del y by del z, which we figured out to be this. So this into y 1 minus y, and finally the xk. So let's say this is wk, right? So then this gets cancelled, so finally you are left with y minus t into x square. So this is a very simple form of the derivative. uh, yeah, oh, okay, Rashmi has raised a hand, so do you have any question?
Yes, sir. Actually, yeah, I can go through the procedure and solve the problems.
Ah.
But within the stipulated time, how to manage it? I mean, if I go
Okay,
somewhere in between, because there are many problems which are like very procedural.
yeah, that is true,
But
that is true,
uh,
because
within the
yeah, so I mean, for the exam I'm hoping you would get problems which are not very long in the process, right? So I'm hoping that you can solve them within the stipulated time. But yes, I mean, the problems will be procedural in a sense, because you are working through an algorithm, right? So, and usually that algorithm is meant to be solved by a computer. But for the course, I mean, for an exam, you have to solve it by hand. So it is going to take more time. Uh, I mean, I don't have any specific tips if that's what you're asking for. I mean, you just
yeah,
have
okay,
to you just have to. I mean, the one way is you can like memorize every algorithm, which you like kind of have to, you kind of have to understand the algorithm. But if you memorize every step, then you can go to the next step very fast without thinking too much about it. But yeah, I mean, the problems are not going to be uh, like the problems are always going to be procedural. So I think that is the basis for this course, kind of. So
yeah, okay,
yeah, I mean, I don't think you should worry a lot about the exam. Like, you will definitely be able to finish it within the time given. Like, it really shouldn't be that complex. But uh, if you are planning to apply any machine learning in your, in whatever you're doing, usually you will apply it numerical, like a computer will do it for you, so you don't need to calculate all of this by hand anyway. So what I'm showing right now is, so this is not like a problem which I'm working through. This is just a concept which I want to clear before I start the example, because you will see this form, like you will see this derivative in the code which we are going to look at. And I wanted to be clear about how we got here, how we got to this derivative. Okay, so anyway, like Uh, I'll just finish this and I'll open up the floor for more questions. Right.
Yes, yes. Thank you. Thank you.
So, okay. So now that I have del J del WK, I can simply update WK as WK plus alpha times del J del WK. Right. So this actually the here it should be minus alpha, but we are doing gradient descent. So that finishes the this form of the derivative, right? So I just wanted to clear this before we got started with the code, right? Do you have any questions uh, that are confusing in this derivation? Oh, okay. So I just asked, can you please explain the convolution problem, which is an assignment 6 14th problem, right? So just give me a moment. 14th problem, stride. Yeah. So an array is given, the filter is also given, the stride is 1. How does the feature map look like after the convolution of input array A with the filter F? Okay, I'll just quickly solve this problem then. So
Are you trying to estimate the error in this problem? Is it for estimating error measure?
oh, the thing which you're seeing on screen, right?
Yeah,
Yeah.
yeah,
So
yeah.
that is a so what we started off with was I have a just a moment. Yeah. So I have a so usually for binary classification, I don't use this cost function which is given here by L. So I don't use this cost function because sometimes it gets local minima and the problem might get stuck. Right, my weights might get stuck. So I use this like a different form of the cost function, and I was trying to find out what del j by del w is if I am using this cost function, right? So this is a slightly different form, and this is more useful in classification problems because usually this function gives a very smooth map, like a very smooth curve with respect to the weights, and I usually have one global minimum where my weights can converge. So this is found to be a better form of a cost function. I was trying to find out what del j del w is, so I can update my weights, right? So that's what I was trying to find out. But yeah, before we get into questions for this, I'll answer the question which was asked in the chat. So the question is, uh, so you have like I'll quickly explain it in terms of like just the concept. You have this your array, right? Your image array, and you have your filter also, just 2 by 2. So what you do is you place your 2 by 2 filter over here, right? So say you place it on this. I should have chosen a different color. So you place it over here, right? And the numbers here are 1001, right? So here you'll have 1001 for the filter, and the numbers on the matrix are something as 7, is it 5, 1 and 3. So you multiply this 7 into 1, 5 into 0, 1 into 0, 3 into 1. So and you add all these four numbers, so the answer is 10, right? So your resulting matrix ka first entry will be 10, right? And then you move this over by 1, you move the filter over by 1, so the filter moves over here, right? So again, so this there's something. So then inside it becomes 1001. Numbers here are 5, this is 3, and there is 3 and 5 again. So the sum here is also 10. So just like this you keep going, so you will have one more for this, one more number here for this row, and then the answer will be a 3 by 3 uh, matrix. So yeah, you can keep filling all of these entries. So it looks like it might be the third or fourth option. I don't know. I haven't calculated all of them. So yeah, you can get your answer from here. Right. Does that clear your doubt? I hope it clears it. Okay. So okay, so we're done with this. Yeah. Any questions on the derivation of the cost function?
So the vanishing gradient, I mean it is not experiencing difficulties of those things, no? Vanishing gradient, what you are trying
This
to do.
this might experience vanishing gradient. I mean, if the it's it might experience yeah. I mean that problem is not solved by choosing a different cost function. Uh, I mean yeah, but so see the problem is that if I had chosen this normal mean squared error, right, what would happen is, so say I would get into my function would start getting into these local minima, right, and there is no way that gradient descent can escape from this area. Okay, so if my weights do end up in this zone, if I'm using mean squared error thing, then once the weights get here, then yeah, so then my I won't be able to take a good gradient descent step out of this minima, right? It is very very hard to get once the weights are stuck here, they're stuck here, right? So yeah, you can call that, yeah, it is part of the vanishing gradient problem. So this new cost function, for classification, it's usually found that, so this creates a much simpler surface for the weights to, for taking gradient descent steps, right? So it does not have all of these local minima, and hopefully it has only one global minimum, right? And yeah, to an extent you can say it's solving the vanishing gradient problem, but it's not, like it can there can still be local minima and my function can still get stuck there. But so for classification problems, uh, we found that that usually does not happen. So it's a better choice overall.
There are other functions also you could have taken, right?
Yeah,
Like
yeah,
you
yeah,
wanted
definitely you could have taken any function that you want.
activation functions, different.
Yeah. Activation, this is not an activation function. This is the cost function.
Okay,
Activation function is this one. Activation function is the sigmoid function, right?
sigmoid function. Okay,
Yeah. Activation is the same. I'm just changing how I am evaluating my cost. So the you can call it a measure of error, right? So I want to reduce this cost now. Like my final goal is to reduce this cost, and the way to do it is by varying the weights. Right. So by varying the weights, I can change my cost and hopefully reduce it over time. So the form of the cost is different for binary classification. That's that's the only thing. So like every other step which needs to be followed in binary classification, like you have your inputs and they go through this one the binary classifier, right? And inside they like we do w1 x1 plus w2 x2, then add a bias, then we do activation and we get this output y, right? Now the thing is, in order to measure how I like basically I want to see how close y is to my actual target, right? So in a binary classifier, the target is usually 1 or 0, right? So there are binary choices. So y should be either close to 1 or close to 0, right? So based on that, I can then once I set my y to be 1 or 0, based on how much value comes out of this. So usually what we do is, if the value of y is greater than 0.5, we'll say that okay, y is we'll set y equal to 1. The my prediction will be equal to 1. And if the value of y is less than 0.5, then we can say that I'll set y equal to 0, right? So that is a threshold. uh, uh, you can change the threshold from problem to problem also. If you increase it, then you will get less y equal to 1 values. If you decrease it, you will get more y equal to 1 values, right? So more positive examples. So but in the example which I'll show you, I have used y equal to 0.5. That is a baseline, right? So okay, let's move to the code. So like you will get a better feeling of why I'm saying all this. So what I'll do is stop sharing this screen, and I'll share my.
So basically, you're doing the error estimating, no?
Yeah, I'm doing error estimator. Okay, my screen is visible, right? So I'll move here. So this is an example in Python, which I prepared. You don't need to understand each and every line of code. It's okay if you don't understand every line of code. Everything is anyway like searchable, and you can search for the documentation of whatever function you are not able to understand. I'll try to explain as much as I can. But yeah, if you have more doubts, like if you have any doubt now, then obviously you can stop me and ask me. If you get some doubts later, then you can look up the documentation. All of this is very well documented in Google. So just it's just one Google search away, right? So let's start. So first we need to import some libraries. We call these libraries, right? The most important of them are this NumPy, Matplotlib, and I have not used this another library called Pandas. So Pandas is a, you can make data sets, like you can make tables and view tables and work with tables. So that is very useful. Uh, but in this case, we are not going to use that. So what I've done is, what I have in this example is that I have a data set of cat images, right? So what the data set wants me to do is to classify uh, if a given image is a cat or not a cat, right? So this data set has images of cats and objects which are not cats. So let's see. So I've obtained the data set from here, from this website called Kaggle. It has a, you can, I mean, if you want to learn more machine learning and start some projects, work with some data sets, then Kaggle is a great place to get data sets and get projects, get ideas to start, right? So first I'll load. So the another thing before you start coding is, always try to write functions in your code, because that makes your code very modular, right? You can like, so this load dataset function, it is not like I have written this function only for this code, only for this example, right? I can use this load dataset function into any of my projects, I can just copy and paste it and it will work. Right, so I just have to change the name of my data sets here. Right, so it is reading some files and it is arranging them in. So I have my training set x. So x is my inputs and y is my outputs. Right, so the outputs in this case is a matrix of only like an array of zeros and ones for each example. Right, and x is basically the image. So it is it so what this function does, load dataset, it just takes this file called train cat v non cat, and it just splits it into the x and the y. So the training set x and training set y. Right, similarly I have a test dataset also, test cat v non cat, and this function just splits it into x and y. Right. So yeah, finally I'm doing some reshaping. This is not important. What reshape does is it. So if you have a 3 by 4 matrix, you can turn it into a 12 by 1 matrix or a 1 by 12 matrix, something like that. Okay, or a 6 by 2 matrix using this function called reshape. And inside you can give whatever dimensions you want. And it is good practice to not always use like static numbers here. So I know that train set y contains around 200 or so examples. So the this value here, train set y shape 0, this value is probably something like 200 or something. But instead of writing that, I would write this, because if I change my data set, then it might not be 200 anymore, it might be 500, 1000, anything. So it is good practice to write code like this dynamically. Okay, anyway, so finally after this load data set function is used, what it does is it gives me four data sets. Right, so it gives me a training x, a training y, a test x, and a test y. Right, so the testing x and y I will keep for later, and the training x and y I will use now to train my machine learning data set, to train my machine learning model. So you can see here that okay, so the this X train original, this has 209 examples, and each of the examples are 64 by 64 by 3. This means that, so this is an image with 64 by 64 pixels, and since it is RGB, it has this additional third dimension, right, which is red, green, and blue. Right, so you can think of it like three matrices stacked like one behind the other. The first one contains red pixel intensity, second one contains green, and third one contains blue. Okay, so in a 64 by 64 matrix, so we'll see an image out of this. So let's see. Okay, so this is one image. This is clearly not a cat, and you see I have also mentioned the output. So the output, the target basically. So this is the target, which is 0 in this case. So if I go to some other number, let's try 60. Yeah, so this is a cat and the target is 1 in this case. So what I need to do is, what my model needs to do is look at this image and find out if it's a cat, and then output either 1 or 0, whether it thinks it's a cat or not a cat. Right, so I have to train my model to do this first. What I'll do is, so I had this 64 by 64 by 3 matrix, right? What I'm going to do is I'm going to just combine all of these dimensions together into one long list. Okay, so it will be, so the size of this list will be 64 into 64 into 3, whatever that number is, it will be 12,000 something. So I will combine all of these into one long array. I'll combine this 3D matrix into one long array, and I'll use that as my inputs. So those 12,000 entries will be x1, x2, x3, x4, all the way till x 12,000 something, right? So this is what I do in this bit of code. So here you see So the number is 12,288. So now I have 12,288 features, and my training set has 209 images, and my test set has 50 images. Right. So this is what I've printed here. Now, if you notice here, I have 12,000 rows, 209 columns. This means that every example is one column. Okay, every example is not one row. Every example is one column. Okay. Now, before I build the model and get started with that, I just want to finish this pre-processing part. So whatever I'm doing now is pre-processing the data. Okay, I'm making this data set ready for my machine learning model. Right, I can't just pick a data set and throw it in a machine learning model and expect it to work. You have to, in this case, I don't have any missing values or anything like that. If you have missing values, you have to try to find to figure them out and try to find what the missing value should be. Okay, so that is another story. So we will not focus on that now. But for usually, if you are trying to implement a machine learning on a data set, you have to pre-process the data set properly and make it ready for machine learning. So the next step in my pre-processing, this is the last step, is to just divide all of the numbers. So divide all the numbers by 255. So the RGB values are in the range of 0 to 255, right? So 0 is for no intensity, 255 is maximum intensity. We want them in the range 0 to 1, okay, because then sigmoid activation can work very, very well. So we want them in the range 0 to 1. All my inputs, I want them in the range 0 to 1. So I'm just going to divide by 255. Okay, so now in my training set, if you see here, I have, okay, sorry, run this. Okay, so if you see here, this is one example of my training set. So this is one column of my training set, and it has so the size of this is 12,000 numbers. There are 12,000 numbers in between these three dots, and each of them is between 0 and 1. Okay, because I have divided by 255 over here. So that completes my pre-processing of my data set. Now my data set is ready. Now I want to build my model, right? So in order to build the model and check if I'm doing everything correctly at every step, I'm defining all the functions correctly. I've defined some small data and parameters. Okay, I don't want to use these 12,000 values to check all of these functions. Okay, I would rather build a small example and just test these functions, and then later I will put them. I'll put my actual data through the model. So I think someone. So anyway, I have my small x, y, some weights and bias values. Okay, so this is my x right now. So these are my inputs, right? So one example is 1 3, and the second example is 2 4. Okay, one example is one column. Okay, so I define my sigmoid function first. Okay, sigmoid is 1 by 1 plus e to the minus z. So if I put it, so if I do sigmoid x, then you see it will take each of these values and put it through this function, right? So 1 by 1 plus e to the minus 1 is this, then 1 by 1 plus e to the minus 2 is this, right? So this sigmoid function is working correctly. Now what I have to do is I have to define my forward and backward propagation. Right. So forward propagation means I have to do so I have all my inputs x1, x2, x3. I have to do w1 x1 plus w2 x2 plus w3 x3, and then uh, and then provide the sigmoid function to that, and then I have to also calculate the cost, right? So these are three things which I have to do. I have combined the first two steps here only. So in this a variable is the output, so is sigmoid of, now this np dot w transpose x, this is basically a shortcut to calculate w1 x1 plus w2 x2 plus w3 x3 like without writing everything out. Okay, this is a matrix multiplication of my w matrix and my x matrix. And the way to do matrix multiplication in Python is you use this np dot dot. Okay, so this takes the dot product. You see, matrix multiplication is dot product, right? So you take the dot product of this w transpose and x, and you will get w1 x1 plus w2 x2 for every example. And I add my bias term also. And finally, I have to calculate the cost in forward propagation. So the cost is I showed you the cost for one example. If I have say like in this case 200 examples, so I just do minus 1 by m into I just sum all of the costs from each example, right? So each example will have some particular cost value, and I'll add them all up and take average. Okay, so that's what my final cost for my entire data set will be. Okay, so here it is the same form. So I have used y for the output here, not t. Okay, I know the notation is getting a bit confusing. Y is the target. So I have my target into log of this thing. So this is my prediction from my what do you call it? My model, right? Plus 1 minus target into log of 1 minus prediction, right? So this is my cost. Now to find the to find del j, del w, and del j, del b also, we need to do this backward propagation. So this is that derivative which I showed you. So this is del j by del z, right? So z is w transpose x plus b, right? So this was a minus y. So if I have to present it from my okay, yeah. So if you see here, so del j by del z is this the multiplication of these two terms. It's in the next page. It will be there. So yeah, so it is this y minus t in this case, or in my case, it is a minus y, right? Then I've called this variable dz. This is del j del z. Then del j del w will be. So I showed it to you for one example. So if I had, where is it? Yeah. So if I had just one weight, then it's like it gets multiplied with xk, right? So for the entire list of weights, I'll take the dot product of x and this dz transpose matrix. You can like you can find out the dimensions of each of these matrices and see that like these dot products will always work. These matrix multiplications will always work, and you will get the correct like size for the w list, right? So the dw will have the same number of elements as w as the weights, right? So in my small example I have two weights only, so dw will also have two numbers, two gradients. And finally db is this value, right? So anyway, don't worry about this line. It removes unnecessary dimensions from the cost. Sometimes you get some empty dimensions due to Python doing some weird things. So this will remove those. I create this. So this is called a dictionary in Python. You can look it up. So it has these keys. So these things in the codes are called keys, and these are the values. So the value can be anything. In this case, the value is an array. This case also db is just a number, I think. So I can make these key value pairs, and I call this dictionary gradients because it contains the gradients dw and db, right? and from this function I want to return these gradients and the cost value, right? So let's see what it does to my small data set, right? So what I've done is I've used these values, these small numbers, to calculate the gradient and cost. So you see the gradient dw is this much, and the db is this much, and the cost is 6, right? So the next step after creating this propagation function, after doing forward and backward propagation, I have found the gradients. So now I want to update my weights, right? So I have called this out. So yeah, nice button. Okay, yeah. So all right. So after finding the gradients, I want to update my weights. So I've done that using a function called optimize. Again, like uh, I have some number of iterations with which I want to go through. So I will calculate my gradients and cost at each iteration, which I can do using my previous function. Then I have my gradients for w and b. Now I can just update it as w is equal to w minus learning rate into dw, right? So dw means del j del w. B is also a similar case. db means del j del b, right? And like, keep in mind that these things are arrays now, okay? So these contain the weights and biases for multiple inputs. So I don't need to write them out for every w. So it's not like I need to write them out for w1, w2, w3 separately. I can do it in this one line, right? So the next step, this is not required. This is just for illustration purposes. I want to record the cost at every 100 iterations. So I'll check the cost value and see if it is decreasing. If it is not decreasing, then I might have a problem. Okay, so I will go back and check my code then, right? And finally, after my weights have been updated, I store them in a dictionary called parameters. My gradients also, I store them in a dictionary called gradients. And I have also stored my costs at every 100 at every 100 iterations in a list called costs. So at the end I'll return the parameters, gradients and costs, right? So this is this function. If you see here, yeah, so it goes through a small, you can say that this is an optimization step, right? So initially the cost was around 6 or something. Then the weights are getting updated at every step, right? So after 100 updations, the cost has come down to 1.43. After 1000, I think I put 1000 here, yeah. So you see the number of iterations is 1000. So after, at the 900th iteration, the cost is 0.46, which is a huge leap from 6, right? My cost went from 6 to 0.46, right? So that is pretty great. My weights have been updated to minus 0.98 and minus 0.191. B has also been updated. So if we go back and check what I started with, so W I had started with 1 and 2, and B I had started with 2, right? But this has gotten updated to W is now minus 0.987 and minus 0.191, and B is 1.8978. So this has not changed much, but still it's a change, right? And the final del W and del B values are also here. So yeah, and there's just one last function which I need to define. This is called predict. So this will take any input, any image which you give it, and it will try to predict if the image is a cat or not a cat. So 1 or 0, right? So again, so this is pretty simple. you just calculate your, so I have been given x, right? I have been given my input x, so you just calculate the output, the your prediction as a sigmoid of w transpose x plus b, right? And finally, so this value is a probability, right? So it'll, so if my probability is greater than zero point 0.5, I'll say that the image is a cat. If it is less than zero point 0.5, which is given by the cells, so if it's not greater than zero point 0.5, it is definitely coming under this category. So then I'll predict it as 0, right? So this is my final function, right? So I've defined how many functions? I've defined from the top, 1 sigmoid, 2, 3, and 4 functions. Okay, it's not a lot. And yeah, so I've checked every function with every with the small values which I had defined earlier. So I know all of the functions are working at least. Like there is no obvious syntax error in these functions, so they are working. Now I'll move on to building the actual model. Okay, so I have all of my functions to build my model. I define a function, again a function called model. So this will take as inputs the training sets, the test sets, the number of iterations. So I have given it a default value of 2000. If you don't mention number of iterations, it will do 2000 iterations. Okay, and learning rate is zero point 0.5. If you don't change, if you don't change this value, then the default value here is zero point 0.5. Okay, so the first step is to initialize my parameters, right? So by parameters I mean my weights and biases, right? So I'll initialize my list of weights with zeros. My bias also has 0. We are starting with 0 initialization. This is not so since this is a very small model, 0 initialization is fine. But if you are building larger models, if you are building some neural network or something, then it is recommended that you use random initialization instead of initializing with zeros. Okay, so anyway, let's move on. Now now that I've initialized my weights, I can just directly, get my final weights and weights and bias, because I have defined all of those functions above. So my work is just reduced to this one line in this code. Okay, so using this optimize function, I can find the, so the optimize function was doing this only. So it was updating the weights at every step, and finding out the final weight and the final bias. So this is what it's doing here as well. So I have my parameters, gradients and costs, and I have my final weights and final biases. Now I can you know pass my uh, like I can use my model to on the test set, right, to see how well it did. So uh, I'll predict the y values for my test set x test. I'll also do a prediction on my training set just to see how well it did. Okay, and I'll calculate the errors. I'll calculate the accuracy basically. So training accuracy and test accuracy. Training accuracy meaning how many of the training examples it got right, and test accuracy is how many of the test examples it got right. Right, the like the percentage. So if you remember, training set had around 200 examples. Test set has 50 examples. So it should be pretty high, I'm hoping. And finally, I'll return some values which are important to me: the costs, the y predictions for the test and training set, weights and biases, learning rate, and the number of iterations. Okay, so this I can return this thing, and I'll have this for further use if I need it. Right. So now that I've defined my model function, I can just run it. So I have my training set, as I've defined before. I have my test set. I have my y train. I have my test sets also. Number of iterations are given 2000 here, and the default learning rate here is zero point 0.5. I have specified a learning rate of 0.005. So if we specify a learning rate here in this attribute, then the default value gets overridden, right? So now it will use 0.005 as the, what do you call it, the learning rate, right? So let's see what this does. So here you see, like, I can see the other cost is going down, which is a good sign. Okay, so after 2000 iterations, training accuracy is 99.04%. Okay, so this means that like 99% of the training examples it classified correctly. The model has been able to classify them correctly, because it is I hope that this value is 100, because like the model is trained on this data set. But 100% accuracy on the training set is kind of not very good. Okay, because it usually means that you have overfit the data set. And the test accuracy here is 70%. Okay, 70% is pretty respectable. I mean, I only had 200 examples to work with, so 70%. And like there are only 50 training, only 50 test examples. If you had more test examples, then for sure this number would also be higher. Okay, so anyway, we'll go ahead. I'm pretty happy with 70%. So we'll see. So I'll just randomly select some. So here I have 49 here. I'll randomly select some example from the test set, and we'll see what the model has classified it as. Okay, so let's see. So here you see, like, this image is not a cat in any way. So the actual target was 0 and the predicted value is also 0. Okay, so this looks good. So let's move to some other example, some random 56. Okay, 56 is not even there. There are only 50 examples. So 40. Okay. Yeah, so this is a cat. The target was 1 and the predicted value is also 1. Right. So let's say 42. Yeah, okay, it classified this also correctly. I'm trying to find an example where it did not classify correctly, maybe. But yeah, looks, I don't know what 70. Oh, here you see, this is not a cat, but the target was 0, but the model predicted it as 1, right? So it has made mistakes 70%. So this is part of the 30% which is incorrectly classified, right? So anyway, I'll plot this. So this is a plot of the cost versus the iterations, right? So it is going down, which is a very good trend to see. If it is slightly spiking up somewhere, then that is fine if it spikes up. But if it, like, just keeps increasing in a very smooth fashion, then that is not a good sign. Okay, that usually means that you have made some error in your code. Okay, so now what one thing we can try to see is, if I change my learning rate, then how does that affect my costs? How does that affect my accuracies here? Okay, so does it actually even matter if I change my training, if I change my learning rate? So here the learning rate is 0.005, and we got training accuracy of 99.04, test accuracy of 70. Okay, so what I've done here, I have chosen 3 learning rates: 0.01, 0.001, 0.0001. Okay, so like 10, 1/10 each time. So we are taking smaller and smaller steps of gradient descent each time. So we'll see how this model works. So it will work through all of the learning rates. It will, like, train the model using all of these learning rates separately. So it has done it for 0.01. I get my training accuracy is 99.52, which is higher than the previous one. Previous one was 99.04, I think. Okay. Uh, but here you see, even though the training accuracy has gone up, the test accuracy has come down. Right? Test accuracy was 70, for now it's 68. Okay, this means that this is a sign that the model is basically overfitting. Okay, in some way, and I would not want to use. Yeah.
Am I audible?
Yeah, you're audible.
Can you share the Can you share the code?
Yeah, I'll
Can you
try
share
to
the
do
link?
that. I'm not exactly sure how I can do that. I can probably put it put a drive link in my in the
No, no.
YouTube video description or something.
Just scroll up. You will get the link. You can share like that.
Yeah, yeah. I mean, I know how to share the files, but I want to share the training and test sets also. So I'd put them in a Google Drive link and I'll share the.
And even I want some old sections codes too.
Sorry, you want?
Old sections. I mean, but the sections already over, like last week sections.
Oh, like you're talking about like these sections of the code.
Yeah, yeah.
Oh, okay.
Uh,
I mean, I'll share the entire code. I'll share this entire notebook with you, right?
like
So.
week from first week section.
Oh, okay, okay.
Uh,
First week. So this is the first example which I'm taking. We have not been working with code through this time. I've only been solving
yes.
problems. So those.
Did you get the recorded
Sorry.
recordings of the problem solving section?
Okay,
Don't
okay.
I get the recordings of the problem
Yeah.
section?
So I think have has the team not shared the YouTube channel link with you guys? So we are all putting. So me and the other TS we are putting the videos up
It is all
in
there. It is
on
there. It is
YouTube,
there.
so you can find all the sessions there only. I'll share
No, I
the
mean
link. Sorry, you are looking for. I'm looking for.
problem solving section. Like we are taking in Zoom meeting. Those recordings, I mean.
Yeah, yeah, I'm also talking about those only. So we are putting them
Those
up.
also I'll get. Can you share that link, please?
Yeah, sure. I'll okay. I'll share it with you. Like, wait, just give me a second. Then I'll share it with you right now only. I'll share the channel link then. Yes, it's okay.
Okay.
So um, just 1 second. Yeah, this is the channel. Right? So just share it here. Yeah, you will get all the videos which I have uploaded here. My fellow TAs are also uploading. I'm not sure, like I don't have their
Okay.
channel, this thing, their links. When I get them, I'll share them. But if you go to your NPTEL announcements tab, I think they have shared the links there also for everyone else
I
as well.
checked it. It's not there. I checked it. I mean,
Oh, okay.
these live classes are not there.
Then I'm not sure how they have been shared with you because other people are able to access it. The like some others who have joined the sessions previously also, they said that they were able to access it. I'm not sure how the team shared it with you. If someone knows, then please
Yeah,
tell her.
No, no, it's all shared actually. It is there. You just go through that. You'll
uh,
get.
Where is it shared exactly?
where?
It's shared in this thing. The main screen. You have got download videos. No, that option that you can just open the course content where you have
Okay,
find all the week
let's
lectures and all.
let's just
Yeah, yeah.
see it.
The
Uh,
last May, end May. Yeah,
huh.
go down. The last one after the six.
Here.
So there is that
Oh,
download
yeah.
problem solving
Yes,
session
they've
also.
added a new
Oh,
tab also, I think. Yeah. So, oh, okay,
Yeah,
okay.
you click there.
oh,
Yeah, you get everything. Just
Oh they've shared this sheet only. Okay, okay. So we
yes,
are
yes,
we are
yes.
updating this sheet every week anyway. So you'll get it right.
yeah. Thank you so
So
much. And share the code also. Don't forget.
yeah, sure, sure. I will put it in the
Only
description
this
of the
week.
YouTube video for this week. But if there is any other way I can share it, I'll share that way also. Okay.
Share through chat box. No.
Okay, okay. I'll do that after I'm done with the code then. Okay. So
Yeah. Okay. Fine.
easy.
Thank you so much.
Okay, cool. So where was I?
So this is all supervised learning only, no?
Yeah, this is all supervised learning. This is just binary
You can have
classification.
an unsupervised example also, where you have a mixture of different animals, and then from that you are picking up a cat.
Uh, yeah, sure. I mean that would be multi-class classification. That is not unsupervised learning.
Multi-class.
Like yeah, that would be multi-class classification. If you want unsupervised, then like it could be like I have pictures of animals, a lot of
Yeah,
animals, and
right.
the model
It
just
can
learns
start
to
from
group
that.
them. Yeah, it just learns to group them. It will not learn ki this is a cat and this is a dog because I have not mentioned it, but it can learn to group these animals into different like categories because they look similar. So I'll do an unsupervised example next week then. I have to write the code for it. I have to find an example also. So I'll do that next week.
No, I don't think you have one. We have exam on Sunday, so
Okay. Then I think you better study for
so
the exam.
this may be the
Uh,
last exam, last class for you. I think so. Or
yeah,
do you
might
have
be.
still classes?
I am supposed to have one more session. I'm supposed to have it, but I will talk to the team
Yeah,
about
tomorrow, right?
what the thing is. No, that is tomorrow's session is not taken by me. So each of
That
us
is fine.
has to take one session a week, right? So I have one more session left. The guy who takes sessions tomorrow also has one more left, like next week basically. Only the TA who is taking sessions on Saturday, he will finish it by this week. So his last session will be this Saturday, the coming Saturday.
So if you can include that
Right.
before the exam, will be better. No? I mean, if you can take it maybe Wednesday, Thursday.
Yeah, sure. Okay, I will talk to the NPDL team about it. Anyway, I have to do one more session, so I will talk to them and see if it can be shifted before.
Because after the exam, I don't think there won't
Yeah,
be any.
yeah. Okay. Okay, sure. I'll talk about it. But yeah, last thing which I want to say is that here in this case, I was using a learning rate of 0.01. I got a better training accuracy. I got a worse test accuracy, which is not a good sign. This means that my model is overfitting. I probably should not use this learning rate. Okay, because this is very high, I would say, for this particular model. If I use 0.001, so you see the cost has not come down as much. So okay, by the way, all of these were run for 1500 iterations only, not 2000 or something. So for zero point 0.01 learning rate, you see that the cost has come down to 0.09, which is very good for the training set. uh, for learning rate of 0.001, the cost has only come down to 0.37, right? So the training accuracy itself is very low, 88.9%, and the test accuracy is 64, right? And if I use a very small cost function, a very small learning rate, 0.0001 is very small learning rate indeed. So you see the cost has not come down a lot. It started from 0.69, ended at 0.57. So that is not a very big change. So you see here the training accuracy itself is very low, 68.42, and test accuracy is 36%. Okay, if you keep running this model, this learning rate of 0.0001 for like 10,000, 15,000 iterations, then you'll probably like you will definitely get better results. Okay, but you want to balance this trade-off between how many iterations I want to run and how high I want the learning rate to be. Okay, so for around 2 to 3,000 iterations, 0.001 seems really good, right? So that's why initially I had chosen a learning rate of 0.005, which is higher than this. Okay, and I also got a better result out of that. In fact, like I got the best result out of all of them using 0.005. Okay, if you see here, the best result meaning the best test set accuracy, because that is the measure of the real world like usefulness of this model, right? So the test set contains data that the model has never seen before, and in the case of 0.005, it was able to classify them with 70% accuracy, which is the highest out of any of these. Okay, so here again I have plotted the cost versus the uh, iterations. So here you see for 0.01 it is actually kind of jumping around the place, okay, which is not a very good sign. Okay, so initially it goes up, it comes down again. Okay, so I'm not very uh, like, happy with this, but okay. So yeah, this has nothing to do with this thing. I think Yeah, this is running the thing for 5,000 iterations. I think I just did it just because I wanted to see what would the final result be. So let's see. Uh, by the way, this is a pretty fast model. If you see, like it's going through 5,000 iterations very fast. Okay. Oh, okay. So this is a very nice number. So the training accuracy is 96.65. So here you see, like this is lower than the value we got for 0.005, right? For 0.005 we had 99 point something something. So the training accuracy is lower, but the test accuracy is higher. I had gotten 70% originally. Now I have 74%. So this definitely means that my model is still kind of overfitting here and there. So I can run it for more iterations and see if it levels out itself, or I can take some other measures also to reduce the amount of like overfitting. So yeah, that's the example. That's it. If you have any doubts, please ask me. Yes. Also, like if you did not understand the code, don't worry about it. If you don't know Python, then also don't worry about it. The code is not what's important. What's important is that you understood the process of how to build a machine learning model. Okay. The specifics of how to build every function and all, that is fine. That that you'll learn as you learn to code properly. So that is not the big challenge here. The big challenge is understanding how I went about building this model and applying it on the data set. Okay, so you guys have any doubts?
Don't you have this in ImageNet repository?
ImageNet is a very huge repository. I don't want to train this model on ImageNet. That will, first of all, it will take a lot of time because it's a lot of data, and secondly, like this model is very small. Like if you train it on ImageNet, then it is probably going to be overfit like a lot, overfit a lot. So ImageNet has millions of images. So if you want to train a very big CNN, then yeah, most of the you get something called pre-trained models. Okay, so pre-trained models are trained on they are trained on all these data sets like ImageNet and all. So if you import them, they will already have some learning built into the model, and you can then sorry, so you can then use your own data set to make that model even better. So that's so that is done quite a lot. It's a very handy tool. Yeah. So yeah, I mean data sets. There are a lot of data sets. If you want small data sets like which you want to work on for your own projects, I would say Kaggle is the best place to get all those. This website, Kaggle.com. Open it here. So yeah. So this like you have code also, like they teach you machine learning as well. You can code yourself. You'll get all the data you need. There are competitions which are held on Kaggle, and a lot of people participate, and they just, and like everything which people write are kind of public. So like you have access to what other people have written in their code. You can learn from it. It's a great place. Like I use it. Even now I use it a lot to learn also, and try to find projects which are interesting, and try to find some data sets. So here you see this house prices data sets, Titanic. So the Titanic data set is like predicting the survival on the Titanic. This is a pretty great example. Digit recognizer. Then yeah, you have a lot of stuff here. So you should definitely explore this website if you want to get deeper into machine learning. Yeah.
Do we need to register for that, or it is free?
Yeah, I mean, you just need to sign in. Like you just need to sign in. That's all. Like if you want to save your progress and everything, then you can sign in. That's it. It is so it works with your Google account. So it's nice. I mean, it's free. There is no fees or anything. It's everything is free. So if you guys have more questions, please ask. Oh, I will open the meeting. See the chat box. I'll share the code. Okay, let's see. I'll share the code. Guys. So, let's call it Notebook 6. So this is binary classifier. Right. Um,
So this multi-class, you can actually again convert it into binary classifiers, right? Many
yeah, multiple
binary classifiers.
classes. Yeah, you can convert them into binary, separate binary classifiers. The easier thing to do is like you just add instead of using sigmoid in your last uh, what do you call it, in your last layer, like in your as a instead of using sigmoid as the activation, you use an activation called softmax. Okay, so that makes your life very easy because softmax is made for multi-class classification problems. So if you just give it the number of classes you have, so you just have to mention softmax 7 or something like that. So 7 is the number of classes I have. So it will find the probability that my prediction is that like so what it predicts is the probability that whatever I gave as input is one of these 7 classes. So it will take it for the first class. Look at the probability that maybe 20% chance that this is. Okay. Tejas, you ask something. Just one second. I'll finish this explanation. Then we move to this. So softmax. What softmax will do is it will say that okay, maybe class 1 has 20% chance. Like this image has a 20% chance of being in class 1, 40% in class 2, maybe 70% in class 4 or something. Okay, so the maximum probability wins there. So if the fourth class has maximum probability, then you say that the image is okay, like this image is probably class 4. Tejasvi has asked, can you please explain question 7 in week 5? So week 5, right? Question 7 you said. Okay, yeah. Oh, okay. So, the question is, what would a greedy forward search give? Right, greedy search means that whatever node you are in, just you always have to take the route with the maximum, like what do you call it, reward, I would say. This is for the first thing, so if you are at S, then your options are you have 3 paths. The path with the maximum score is 6, so you take this path. Then you reach C. This is only one anyway, so you reach F, and then from F again you have only one path to get to T. Right. So this is what it would give, I think. Right. Yeah. So that would be 14, right? Yeah, I mean, I don't know what happens.
26,
Yeah,
26.
it's if you add it up.
26.
Oh, but the okay,
That
the
is
accepted answer is
4,
26.
12. Ah,
But how do you get 12? I mean, the first path you take is this, right?
4, 12, and 10.
4,
4
12,
is
and
very small,
but
no? Yeah.
oh, okay. I was taking the maximum value at
No,
every
no, no, no.
step. Okay, okay. I have to take the minimum value. I'm very sorry about that. So, yeah, so at every node you take the minimum uh, value of the path and then you proceed. So in this case, it would be 4, and then at B, when you reach B, then your options are 18 and 12. So 12 is smaller and D is 10. Yeah. Yeah, yeah, yeah. Okay, okay. Thank you for correcting that. Question 6 in
Question
the
you were
same
explaining.
assignment. One second. Question 6 in the same assignment. What is this? Choose a correct sequence of phases. So this is for
What's again?
case-based reasoning, right? So this graph was given in your in the presentation slide itself. Uh, what is it? So it would be retrieve,
B, the last one.
revise,
No,
reuse,
no. Retain,
retain.
retrieve,
Okay.
revise, and reuse. Yeah.
Why are we start? Okay, one second.
It is
I
revised
did
case is
not look
stored,
at the
no?
question also properly. One second. X is store. Y is acha. Okay, we just have to mark these. Okay, I thought we had to like choose the correct sequence of steps. Okay, so yeah,
Storage, retain.
revised case is stored in the case base, so that is retained, right?
No, it is retrieved. Retrieved
Then
from the case.
X, Y
Retrieve.
case base, you retrieve a relevant case. So Y is retrieve. Relevant case, you move to revise. So this is basically revise.
Revise,
And
right?
revised case, you apply to a new case. That is, yeah, that is reuse. Yeah. A relevant case, you apply to a new case. I think that is the what I want to point out here. Yeah, so that is reuse. So this arrow is going from relevant case to new case. Yes. So this entire graph is given in the presentation slide itself. You can look at it.
This softmax example is there in which topic? Relate?
Softmax. I don't know. No, I don't think you will get a question from it. Like you will not get it in the
No,
exam.
no. It's
Uh,
it is
prof-
actually there in
the
in the
professor
in
has
the
mentioned
this
it.
thing.
It
Mentioned it.
is there. Yeah, it has. He has mentioned it, but I don't think you will get a numerical example from it. Because, calculating it numerically is
Mm.
very difficult. The like
Okay.
the formula for softmax is very intense, so it is it is very difficult to calculate by hand.
But in which topic will be that? I am not getting it.
I forgot the actual lecture. It would be somewhere in neural networks, somewhere in that area. Somewhere in ANNs, maybe he has mentioned it. I'm
Yes. I
forgetting the
don't think I'll
exact.
be able to
Yeah.
remember. That's okay. I got it.
So I've shared the code, by the way. There's a drive link here. If you want to download it, you can go ahead and do that. But I will also put this in the YouTube video description here.
So it is said that multi-class classification problem can be reduced to multiple binary classification problems
Yeah,
and can therefore indirectly be solved by parallel multiple perceptrons.
yeah. So basically, parallel binary classifiers. Yeah. So you can, like, your inputs will all be the same, and you have different binary classifiers which are trying to classify. So one might be trying to classify if it's a cat or not a cat. Second one is trying dog or not dog. Third one is trying. So your labels would be different. You have to like so a binary classifier can only do 0 and 1. So in the first case, when you get your data set, in the first case, like you have to uh, so in the first case, you have to set your outputs to be 1 when the image is a cat. Okay, in the second case, you have to set your outputs as 1 when the image is a dog. So you have to modify your data set for every binary classifier, which is very involved if you have a lot of classes. But if you are using softmax, then that is not required. If you are using softmax, then you will have one output column which has a class number. So 1, 2, 3, 4. So if I have 4 classes, then the output will be either 1, 2, 3, or 4, right? So softmax can automatically calculate probabilities for every class itself. But for multiple binary classifiers, you have to like change, like modify your data set, modify your outputs. Okay, guys, are there any more questions?
The kernel trick you can explain once more. No? That is nonlinear
Sorry.
kernel trick. That is SVM to linear and non-linear.
Okay.
Support vector machines.
Okay, just 1 second. So,
Yeah.
I forgot where SVM was. I forgot the kernel trick actually. So because I haven't
Yeah, I'll tell
applied
you
it.
where it comes.
It comes in week 5 or something.
No, no, week 6.
Does SVM come in week 6?
Or week 5.
Can you tell me which lecture it was in? Week 5 was
Yeah, I'll check.
explanation based learning, case based reasoning, reinforcement learning. That's it.
I'll just check it.
Inductive logic programming. I forgot where it was. There were a lot of concepts which are taught here. Even I was not aware of a few concepts.
So, week 6 maybe.
Week 6 has. I don't think it's in week 6. I'm not sure where it might be. No, after this, I'm pretty sure it's not there.
It's okay. I mean, that is a non-linear case you are trying to classify, suppose, uh,
Hmm.
in a kernel.
Hmm.
Kernel trick is
Hey, you're not audible anymore.
yeah, there is that
Yeah, yeah.
MOS thing going on. I that's why.
Ah, okay, okay. Oh, Navas. You say that's another question. Is there an advantage of using softmax versus multiple binary classification in terms of big O of n or computation? So, mm, okay, first of all, I would say the advantage in terms of O, probably softmax is probably a little bit more um, like I think I am not. I have no idea about the complexity, about the time complexity of this softmax or binary classification for that matter, because I am not very well versed in these topics. In terms of efficiency, like in terms of computational efficiency, softmax is definitely faster than multiple binary classifiers running at the same time. So yeah, if you want to think about it like that, I can definitely tell you for a fact that one softmax, you have only one network then, right? You have only one network which is running softmax versus like 10 networks which are running 10 different binary classifiers. So the softmax one is definitely faster than that. Plus you have to do so much extra pre-processing for those 10 binary classifiers. It is not worth the time and energy and money for that matter. Yeah. So I mean, multiple binary classification is almost never used. So multiple binary classification is just a bad idea compared to doing a simple multi-class classification like using softmax or something.
This was in week four.
Okay, so then week 4, right?
It is a numerical also is there in that, and week four actually has got this lecture.
Week 4, 4.2 maybe. Oh, this is generalization as such. This is mm, where
Not
is it?
decision trees, not that.
Not decision trees. This one is decision trees part 2. I
No,
don't think it
week
is
four
there
has.
also.
Uh,
Then there's
in,
instance based learning.
yeah, in this we may find
Ah.
kernel trick.
Oh, okay, okay. Yes. Uh, yeah,
Yeah,
yeah.
this one only.
Um, hmm, yeah, true. Non-linearly separable. Uh, so- oh, it is talking about this. Right,
That
right,
is a trick.
right. Yeah.
where you have this first second case is in a three dimension. He has actually taken. He has added one more
Huh.
extra dimension so that it is looking like a binary linear classifier.
Yeah, yeah,
Non-linear thing is
right.
converted to linear by taking a third dimension.
Yeah, by adding a third dimension, yes. Okay,
That
okay,
only is a kernel trick,
that's
is it?
yeah, 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 yeah. Oh, okay, okay. So basically, like what they're doing is, uh, kind of you could say they're modifying the like my what I consider as my inputs. You can say to my SVM, right? So I will also have my data points as my inputs to the SVM, right? And it will figure out the decision boundary. So instead of just giving the xy points, the xy coordinates, maybe I can give x1 like x1 square, x2 square, and the square root of 2 times x1 times x2. These three as my inputs, and that will help it better. So if I introduce some non-linearity in my inputs only, then it can help with finding out, because like SVM, the algorithm of SVM is a linear thing, right? It is not adding any non-linearity by itself. So if you add it yourself, then that is the kernel trick basically. So you add some non-linearity to your SVM yourself by adding a third dimension, by changing what you supply as input. Something like that. Yeah.
So we are
Yes.
instead of considering the XY plane, we are taking the XZ plane, right?
Yeah. Yeah. So yes, that's right.
Then it visually looks like it is a separate
It's a separate. Looks like a separate.
separated.
Yeah, yeah, yeah. Visually, it will look separated. So you make your SVM solve a related problem, kind of like in a higher
A
dimension.
linear
Yeah.
linear classifier product.
Yes.
Suppose there is one more dimension. My
Huh.
question is, if there is extra dimensions,
Yeah.
then it's suppose a three-dimensional thing. It can be made into
It.
four-dimensional.
Yeah. That can be done. I mean, you won't be able to visualize it, but yeah, it is possible.
Okay, but what about the other things? Like there is some other. If you go to slide 15,
Huh. Yeah.
or I think it is no, no,
Here, if you
some slide.
want.
Yeah,
Yeah.
this one.
Yeah.
Yeah, what are these other things? This
These look like, these look to me, these look like proteins. I'm not sure what these images are. 1 second. So, I'm not even able to read what is written here. Can't edit this.
no, these are I think the names of those things.
Okay, I think these are some crazy decision boundaries which people have come up with and given names to them. Like maybe the kernel trick which you use for getting this sort of a decision boundary is called this arc repressor or something. Then yeah, these I
No,
mean,
no, 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 no.
honestly they look like protein structures.
Yeah, there are different structures. So it has some instance spaces of raw instances expressed in other forms.
Huh,
That is
okay.
the second thing. Instance spaces with raw instances expressed in other forms. These are other forms of expression.
Okay. Maybe
Like
separate.
the non-linearly separable spaces is the first example. The
Hmm.
second space is the instance spaces with raw
Raw instances
instances expressed
expressed
in
in
other
other
forms.
forms. Okay.
Yeah, that is the
So
relevant case.
uh,
So you are able,
I
you are
have no idea
you are
how I
expressing
would.
it in it's a some biological thing. So
Huh.
it is
Yeah.
some instance spaces which are expressed in other forms. So
Yeah.
different forms. Like
Yeah. Exactly. Like I have different proteins. How would I classify them based on some
it is a
criterion?
non-feature vector data case. Yeah, yeah, based on some criterion.
Hmm.
Non-feature vector data cases.
I mean, at some point, I would have to convert these proteins. I mean, I could use the image, obviously, but at some point, I would
So
have to
some
convert
binary.
this into a feature vector to even pass it through my SVM in some way. I'm not sure. I mean, you could look at the features of the of this protein and this protein and find out, like, look at some similar parameters. This is some parameters which you can use to classify proteins, I guess. You can look at that and try to make a feature vector out of it. But I'm not sure how to explain the kernel trick here to you. Not sure how it is applicable.
He says it's they only require a distance or similarity measure. So if you can
Function.
find the similarity measure between them, means maybe that's separated by that distance or some.
Yeah,
Uh,
maybe you can find the, like, something like the length. That might be a, like, or maybe you have some baseline protein and you measure how different the other proteins are from this baseline protein in some way, like using some features of proteins which I have no idea about. So
hmm.
yeah, I mean, it'll depend from to from. But at some point you will always have to, if you have been just given a data set of proteins and you have to classify them based on some criterion. I mean, you can't just use the protein images. I think you also need to have some more information about the proteins, right? There are a lot of features of proteins, so maybe those are given to you and you use them to and if you see that it's a very non-linear decision boundary which is happening, then you can try. So you have your protein feature vectors in a way, and then you can use the kernel trick easily, like the first case. So you transform this case into this case and you solve it, like you do for this case, right? You apply the kernel trick and find some better similarity measure. uh,
No,
that
if it
is
is
that is something I can
if it
think of, but
if
sure.
it is just adding a dimension, that is okay. But here
Yeah,
we have to do something extra, is it?
here, like, here your instances only are in some weird format, right? So the
That they are non feature vector
they are
databases.
non feature vector data cases. But so, like, okay, I'm not exactly sure how without a feature vector. I mean, if you consider the protein as an image, that is all that also becomes a feature vector. Like the matrix, the image is basically a matrix, no? So that matrix becomes your feature vector. You can call it, right? So, like, and then you can pass that image through your SVM and look at, and look at the result. But I mean, you can get a decision boundary, but I don't see how you can solve a problem without first making some sort of feature vector out of it, right?
What I mean to say is you're taking the first instance, and then we are trying
Huh.
to check with the other instances.
Hmm.
Uh, so something will come out in that. I mean, maybe that instance and the corresponding instance when we are trying to compare,
Hmm.
then it can lead to some kind of a kernel trick.
Oh, yeah. I mean, yeah, that is yeah. That's what I said once, right? Ki you have some protein you are comparing
Let's
the
take
other
the
proteins
first
to.
instance.
Huh.
Yeah,
Yeah.
comparing that with
Huh.
other instances with.
Other instances you are comparing them, so, and then you get some sort of similarity measure, and that way you can apply the kernel trick. Yeah, that is one way. But in general, but yeah, now the question is, like, when you have this baseline protein, so say the first protein is my like,
Mhm.
is something that I want to compare the others to. What do I compare among these proteins? I mean, I can compare the images, but the images are obviously very different. for every
There are
protein.
different colors. There are different
Ha,
colors and
exactly.
structures also.
So you have to extract these features from your proteins, right? So every protein will have some particular colors, some number of hydrogen bonds maybe, then some amount of what do you call it? I don't know, the curling of proteins. I don't know what it's called. Uh, so I'm forgetting the technical term for it. But yeah, so all of these things you can. So you are basically making a feature vector for every protein, right? So whatever features of that protein I want to see, then you are comparing this one protein to every other protein, right? And you get some sort of similarity measure out of that. So I mean, at the end of the day, you are still converting your non feature vector examples into some sort of feature vectors, right?
Yeah.
So that is definitely there. uh, I don't think I'll be able to answer better than this is because I also have no idea about what is happening with with this particular instance in this particular case. I mean, if the professor had given some other example, maybe I would have been able to explain that. He has also not mentioned it anymore. Yeah.
No, no, it was a superficial touch, but
Ah,
it's
yeah,
nothing.
yeah,
He has also explained about it, so
yeah.
I don't think we need to bother also. So
I don't need to
it's
worry
fine.
much about it.
So suppose convolution, two functions are given and we are expected to get a third function,
Huh.
right?
Yeah.
So if it is a simple thing, we can compute, but it's like reversing the first one and
Usually,
then just trying to add and like
usually,
that will
if you are given the graphs, no, like graphs of the functions,
yeah.
then it will mostly be simple shapes. I'm hoping. But if you are given functional forms, then just use the formula, right? That is easier instead of trying to draw the function and calculating area like that. Just use the formula. Like you've been given an f of x and a g of x, right? So you all you have to do
The
is
formula of
integrate.
minus infinity to
Ha,
infinity,
minus
that
infinity
one,
to
that
infinity.
integration,
Ha, that integration. Just do that integration.
f of g.
Yeah.
No, but it comes, it's a, it will be also, many steps in that, even it's the simplest of the thing,
Yeah, it
still
will be
it's
complex,
lot of,
obviously. I'm hoping that they don't give you them like very difficult functions. Like,
no, they won't,
huh. If
they
they are
won't.
giving
I mean,
just
yeah,
graphs of the functions, then I would think they'll give very simple, a very simple curve,
uh,
maximum circle or something they might give. So
no,
yeah.
it can be this example of, this is one question from the exam paper, old ones. So that is like, suppose there's a rectangle and a square, you end
Huh.
up getting a shape of,
Trapezium.
what trapezium, yeah, trapezium.
Yeah,
Yes,
it will be a trapezium.
the,
So
it
when the
will be a
square is
trapezium.
entering and when the square is leaving, those are the parts where the area is varying. Other times in the middle, when the square is inside the rectangle, then there is no change in overlapping area, right?
So that is 1 to 3 is no change, but 0 to 1 and then 3
0
to
to 1
0
is
is
when
that's
I mean, the side of the square is
inside.
1. What
Hmm.
I am guessing from this. Side of the square is
Yeah,
1.
correct. That one.
So when it is
Side of the
entering
square is
from
1.
0 to 1, when x is between 0 to 1, so when
Hmm.
the right end of the square is between 0 and 1, that time the square is
Hmm.
entering, right? So the overlap area is increasing, then it remains constant, then it
So
goes down.
overlap area
Yeah.
is actually cut off, right? I mean, like it is like reversed, right? If you,
Meaning,
I mean, I just want in a layman's term, suppose if the second function is entering, it has to be reversed and then integrated is added in that sense. Correct, na?
yeah, but even if you keep the square fixed and move the
Hmm.
rectangle, right? So
Hmm.
the area of overlap is the same at the end of the day. So when the rectangle is moving through the square, so when the rectangle is entering the square from 0 to 1, there will be a variation, right? Then from 1 to whatever the length of the rectangle is, there is no variation because the square, like the area of overlap is the same, right? I mean, it's
But it is moving from the negative direction. There is a negative axis also, no?
no. So when say your
There is
f,
interval.
so say your f is the square, your g is the rectangle. Okay, wait. I'll open that. Uh, I think the annotations are gone there. But, okay, fine. So
Last week, I
yeah,
think you explained.
yeah.
Yeah.
So my f is the rectangle, g is the triangle, right? So when I'm doing f star g, I'll flip this triangle and move it through
Yes,
the,
flip the triangle and
huh,
move it.
move it.
Correct. But that
When I'm
where are you moving
doing
it?
g, huh, but when I'm doing g star f, I'll flip the rectangle and move it through the triangle, right?
Yes,
Yeah. So I mean, there should not be any difference.
both ways. Huh?
Yeah, there should not be any difference either way. I mean, for simple functions like this, there is definitely no difference because even if the rectangle, so if the rectangle was here and it was moving through, so it's a rectangle. So the rectangle was here and it was moving through, right? So it is moving like this. So then the area of overlap, like it comes till, so when it just starts, it's increasing in a parabolic fashion. It will increase this for the triangle. Then from here till here is the same overlap, right? Because the triangle is inside this rectangle. Then when it's leaving, then the overlap area starts decreasing again, right? And then it leaves. So the final result is the same, I think. Yeah, yeah. It will be the same.
So, what's the final result of this?
I forgot the answer to this question. Now I
It is
have
also a
to.
trapezium.
No, so for if the triangle is moving in, then it is sort of a parabola. Then like instead of the trapezium having straight sides, it has like parabolic sides. It is yeah,
Yeah. That
yeah,
correct. There's a parabola rising and down, coming down. Yes,
yeah,
that shape.
yeah. So it's when it enters, that parabola is x square by 2, I think. Yeah. The
Hmm.
formula for that parabola is x square by 2.
Yeah.
Then it stays constant. Then it comes down to be 4 minus x whole square by 2, I think. Yeah, yeah, yeah. That one.
So there is a difference between convolution, cross correlation, and autocorrelation. Huh?
All these three are different things. Cross correlation and autocorrelation are related, but convolution is different from either of these.
There is a comparison
There is
between
the professor was comparing them. I think I was
yes,
not pay much attention to it.
yeah,
But,
in the sixth week,
in the sixth week, it is there. I
sixth week.
remember. Yeah, it's there when he starts talking about convolution and everything. Yeah, it's there somewhere. I don't remember exactly where, but it is definitely there. So convolution as
Yeah,
defined
this
in
one only.
mathematics. Yeah, here only. I think he has
Yeah,
mentioned it somewhere.
correlation and autocorrelation.
Yes. Here. Yeah. So in correlation, basically you don't flip this triangle. You just like in cross correlation, you just pass it like directly, like in this shape only. In convolution, you would flip this triangle and pass it, right? In cross correlation,
Hmm.
you don't flip it, like you just pass
He
it.
says they are both the same. It's similar to cross correlation.
And related to autocorrelation. It is similar to cross correlation in the sense that like this triangle is passing through this like square, just that it's not flipped. Autocorrelation is for, so autocorrelation is
It is
when the two
flipped, na?
objects are similar, like f and f. So it's like square. This square passes through this square, and this triangle passes through this triangle, like that.
No, it is not flipped, but it is passing. Yeah, it is
हाँ,
flipped or it's passing.
कॉन्वोल्यूशन
It's
में
flipped.
द ट्रायंगल इज फ्लिप्ड एंड पास्ड. क्रॉस कोरिलेशन में द ट्रायंगल इज नॉट फ्लिप्ड एंड पास्ड.
Okay, but how it is same?
I mean
Result
the
is the same, is it?
no, result is also not same. They are different things. The results are different for each of them. Each of them is different. But they're just related. I mean the concepts are similar. You know, the results are different for all of them.
Mhm.
So cross correlation. So F like F cross correlated with G is not the same as G cross correlated with F. Okay, so it's not like that identity that, does not hold. What do you call it? Commutative, I think. Yeah. So it's not
Mhm.
commutative. Convolution is commutative. F star G is the same as G star F. Here you see like they run F star G, they got this graph. G star F also they got same graph. But for cross correlation they got different graphs. And autocorrelation anyway is like same shape, so anyway the answers are different.
Autocorrelation is same
Huh,
function.
same function. Yeah. Autocorrelation is also is always the same function.
But this G star F is equal to F star G is in this cross correlation, no?
No, it's in convolution. It's not the same. You see the graph, no? Here for for cross correlation, G it's also star
Star
only.
F.
What can I call it?
Hmm.
It's so G star F for cross correlation is like this small parabola and then this huge thing. But F star G is the opposite of this. So it's different. It's a different result. For convolution, both of them are same.
Okay, this same. Right. Okay.
Okay. Uh, so it's we way past the deadline. So anyway, are there any more questions?
Try to squeeze in one extra class,
Aha,
and
yeah,
it will be good
I'll talk to the
this week.
people and we'll try to figure out. Okay, then
Yeah,
I
thank you.
guess that's it, guys. So yeah, all the best for your exams. I'll
Thank
try
you.
to squeeze in another session before that. But if I'm not able to, then yeah, all the best, and yeah, I hope you learn from this course. Yeah, see you guys.